All right, so now that we've learned a lot about our nuclear reactions, I wanted to come back to our band of stability here, right? So our band of stability is really, right, what we're looking at here is our atomic number, which is our number of protons, versus our number of neutrons, okay? You guys in your notes have a slightly different one that might be a little bit more clear than this one. But what we have here is all of the isotopes that we know of, and we have some that are in dark that you guys may or may not be able to see, but on yours, right, they're darkened because those ones are the isotopes that are stable, okay? And we've learned about 3 different types of radioactive reactions, right, nuclear reactions. So we have alpha, beta, and gamma reactions, okay? And so if we look at this band of stability, what we see is that the elements that are, or the isotopes that are going to undergo alpha decay are up here at the top, right? The nuclei are really, really big, and so the nucleus doesn't have enough force to hold on to all of the particles. So it's going to get rid of some of those particles by undergoing alpha decay. All right, it undergoes alpha decay so that it loses a mass of 4, 2 protons, our helium atom, right? We lose 2 protons, 2 neutrons. We end up making the nucleus smaller, right? For beta decay, right, what we're doing again is we're changing a neutron into a proton and an electron, right? We split it into those two. The electron gets kicked out. So we end up writing that we lose this particle here, right? So an example of this would be something like carbon-14, right? Carbon-14 is going to be down here, okay? We've got a mass number of 14, only 6 protons, so 8 and 6, so we're going to be down at the bottom here, but we are above our stable isotopes. So our example, right, we've got carbon-14, we lose, -1e, we lose our electron out of there, the neutron is converted to a proton, so our mass doesn't change, but our protons becomes 1 higher, we end up with a stable nitrogen atom, okay? So in this reaction, right, what we're doing is we're taking our number of neutrons, bringing it down 1, and our number of protons up 1. So really on this graph, we're moving in this direction when we do a beta decay. So if our isotopes, our unstable isotopes, are above the stable isotope line, so those are our darker dots, we're going to undergo beta decay over here to move towards those stable isotopes. But if we're below the stable isotope line, say we have 50 protons, 50 neutrons, right? We're down here. We don't want to move in this direction because there's no stable isotopes in that direction. Instead, we want to move in the opposite direction. So what ends up happening is really we do the opposite of beta decay, and we do what's called electron capture. Okay, so let's use that same example. If we have 50 protons, 50 neutrons, we've got a mass of 100, and this is tin. This is an unstable isotope. So it's going to undergo electron capture. So rather than our electron being over as a product on the right-hand side, our protons in the nucleus of the tin are really pulling on the electrons, and it's going to pull so strongly on one of them that it's going to suck it into the nucleus, and it's going to form a neutron by combining the electron and the proton. So let's draw that exact same symbol, right? We're going to pull that electron in, and then we're going to end up with a different nucleus, right? We don't change our mass number because our neutrons and protons weigh the same amount, but our protons, we took one of those protons and we combined it with this electron. So 50 plus -1 is 49. We have lost one of our protons and converted it to a neutron. Okay? So this is electron capture. It's basically just the opposite of beta decay. So when we are below our stable isotopes, we're going to undergo electron capture. Okay? You really can't read that, so I'm going to rewrite it down here. Okay? So if we're below the stable isotope line, we're going to try and move in that direction, generally by undergoing electron capture. Now, what about our gamma decay? For our gamma decay, it's kind of hard for us to know when we're going to undergo gamma decay just by looking at this here. Because with gamma decay, we're not changing our protons or our neutrons, okay? So we're not changing those, so we don't know which direction we want to be moving, okay? Oftentimes, gamma decay actually happens at the same time when we undergo alpha or beta decay or electron capture, okay? So our electron capture is really just one type, or is just kind of one type of radioactive process that can occur, and it's the opposite of our beta decay.